Good afternoon. Hello, everyone. My name is Lukas Lücker, and I'm working at the TU Dortmund University at the chair of Materials Test Engineering by Professor Walther, and I'm presenting non-destructive direct current potential drop assessment of forming-induced pre-damage of AC 5115 steel. Some of the results were presented or were part of a master thesis of Lars Lingnau. He's now also working at the WPT. So just to let you know what you can expect from my presentation real quick, I will start with the motivation, then tell you about the materials and the methods I'm using, and then present my results and discussion. And at the end I will give a conclusion and outlook for the upcoming task. Here you see forward road extrusion parts of the process with different shoulder opening angles. I will tell you more about it later on. So coming to the motivation, during metal forming, strain hardening, residual stresses and damage occurs and limit the forming process. We know a lot about strain hardening and residual stresses. It is well known that we know a lot about the influence on forming, but we don't know a lot about damage and the influence on forming. So we know that damage occurs way before failure. So here it starts with the void formation, goes to the micro crack, and then we got a macro crack, which is defined as a failure for the industry. And the industry right now is not interested in damage-controlled process design, but wants to maximize the extrusion strain to get more output. And we, as a research group, the TRR, SFB, TRR, schädigungskontrollierte Umformprozesse, want to change it. We want to have a damage-controlled process design, which gives us the possibility to do or design safer parts due to higher tolerance, and even enables the possibility to for lightweight constructions. And my sub-project is asking the question, and I try to answer it, how can damage at a micro scale in form of pores and microcracks can be correlated with measured variables at the micro scale. So I want to non-destructively characterize the pre-induced damage of the forming process and its influence on fatigue behavior. So next I want to show how I want to do it. First I need to measure a characterizing measurement system or method, and I choose the electrical resistance measuring system for this presentation. And I used source measurement unit of and a nanometer showed here from the company Kately. With this measurement unit I did on round specimens, added the current at the front, and in the narrow space of the specimen I applied the voltage measurement. I know a lot of you know the basics, but it's really important, so I just talk about them real quick. So we want to know the R, or the resistance, and then we're measuring the voltage. To get the R, we need a really highly constant current. This is why we need a really good measurement system, to get a highly constant current that we know. The resistance is divided in, or is upon a specific resistance and divided in a specific resistance and a geometrical resistance. The geometrical part is defined, or I eliminated it with the same specimen geometry, and the specific part of the resistance contains, since the Memphis rule says that we have a thermoelectrical effects part and the non-temperature dependent part, which is defined from the microstructure, for example pores and microcracks, which is the part I'm really interested in. So I want to measure this part, and to do the show I need to eliminate this part, and I do this with the delta mode. The delta mode is to apply an once alternating current and measure the voltage, because of the specific resistance dependent on thermoelectrical effects. Don't know polarity, so you can eliminate this. Since you know the resistance or my method, I want to talk about the material and the forming process. I'm investigated case hardening steel AC 5115 with the here shown chemical composition. For this investigation, I choose the process, the forming process forward road extrusion. This process is done by pressing a workpiece through a die with a punch, thus reducing the diameter. The advantage of this forming process is that we have on the center axis the same stress ratio, or the same strain rate. If we just verify the shoulder opening angles, and this is what I did. We have two different parts, one with a shoulder opening angle of 30 degrees and one of 90 degrees. You can see it here, this shoulder opening. And the big advantage of a big research project is that we have a lot of sub-projects that are working, and I get the knowledge of it. So another sub-project provided me this data of the void area done, or void or pore area. It was measured in the 2D SEM, and the 30 degrees, the part with the 30 degrees shoulder opening angle has a 76 micrometer square and pores, and the 90 degrees 302 pores, micrometer square. So we have a lot more pores and damage on this particular part. In process simulation, we see that on this axis, in the center axis, the strain hardening and the residual stresses are pretty comparable. So, thus we have found a forming process where we have only variate the damage and not other microstructural effects. So we took this part with 30 and 90 degrees and did a specimen, or took a specimen out of it with this geometry, and I applied a newly developed test setup where I developed a swing-controlled contact to have always same contact pressure, so the contact pressure is a really big influence on the measurement of electrical resistance measurements. And I also got a constant distance between current input and output, and have the same measurement rate. So with this system, I was able to do highly reproducible, fast and non-destructive measurements. Coming to the results, starting with the microstructure, because it's the basis of the measurement. Up here we have SEM picture of the shoulder opening angle of 30 degrees, and down here the shoulder opening angle of 90 degrees. I don't know if you can see it, but on the 30 degrees there are way less pores than here. I mean, this is just a picture, but the other sub-project showed it already. And also I did some EBSD scans for 30 degrees, 90 degrees, and also for the initial state, shown over here. And we can see that the average grain size is reduced by the factor of 2 almost. And we see that there's no big difference in the shoulder opening angle of 30 and 90 degrees. Both have an average grain size of 10 micrometer. Also I did some hardness measurements throughout the specimen, and we got for both states the hardness about 190 HP. Thus, the microstructural properties which are affecting the electric resistance are comparable in both states. So now we apply the electrical resistance, and this is plotted in this graph. Show the electric resistance over the shoulder opening angle. I did the measurement with the data mode, just explained, and some optimized measurement parameters, which was a lot of work, but yeah, doesn't fit in this presentation. I did for every state 4 specimens several measurements, and we see in each specimen very low scattering. I measured along about 10 minutes and got a really low scattering from 5 nano-ohms, and we got minor difference within each state, which is due to different pore distributions. But still, of the minor difference within this state, you can clearly see that there's a tendency to have, if you have more pores or more damage, pre-induced damage, you got more resistance. So thus you can say that characterization of forming induced ductile damage in form of pore volume by the means of resistometry is more than possible. And then in earlier studies it was shown that the pre-induced damage has a significant influence on fatigue, the fatigue behavior. So I wanted to add the non-destructive method to the fatigue, to fatigue tests. So I investigated the specimens you just saw with fatigue tests, and measured the resistance with the same test up at 25%, 50 and 75% of lifetime, and plotted the results in this graph, the relative chance of electric resistance to compare those results. You see there's a pretty comparable material reaction, but the 30 degree with less damage shows a little bit more of an electrical increase. So thus a characterization of fatigue damage in form of microcracks by the means of resistometry is also possible. Due to the time, let me just quick summarize what you just saw. Damage has a great influence on the mechanical properties of formed components. We need a reliable, time-efficient and non-destructive test method, and we did it with the electrical resistance measurement. the microstructural properties affecting which are affecting the electrical resistance are comparable in both states. So the difference in DC resistance can be attributed to the damage. And we got a characterization of the means by DC resistometry of first the forming-induced ductile damage and the fatigue damage. The outlook I want to do is I want to combine micromagnetic and electric resistance measurements on one system. I did the same investigation with micromagnetic investigation, so the results are pretty comparable, but I want to combine those to separate some effects. And I want to investigate damage on the pre-induced damage influence on the FHCA behavior. Those are some publications. If you want to read some or have one, just please contact me. You can find more on the homepage. Last but not least, I want to thank the DFG for founding this project and its financial support. And then I thank you for your kind attention, and we'll be happy to answer your questions.
For your very interesting presentation. Do you have any questions? Yes, please.
Thank you very much for this very interesting presentation. Perhaps I missed it, but you don't tell the distance you have between your measuring points.
I don't have it on this. I don't have the backup slides here. It's like. Let me see the.
It's just a question of 1 millimeters, 10 millimeters.
No, it is. So this is the voltage is about 10.
About 10 millimeters.
Yeah.
Because the accuracy of the potential drop method increases with a smaller distance of the probe. So perhaps you can enhance if you get closer, the current or the measured voltage gets smaller, but the resolution gets higher.
Gets higher. Okay.
So perhaps you can
really,
enhance.
that's a really good thing. Thank you.
Thanks.
Any other question? Okay, if you allow me, I have one from an absolutely non-expert. My one year was in an interesting presentation of Dr. Bell, and I asked if the thermal camera could inform about the thermal eventually heating zone by the current and the voltage in that zone. Naturally, when we apply a current, will warm up a little higher than the remaining part, where you have hypothetical internal defects. You consider that would happen?
So I didn't get the question.
I was wondering if instead of measuring the voltage, you could obtain the temperature and
to measure the temperature and you
when
can
applying the current locally in that zone that could warm a little more, and using a high sensitivity thermal camera obtain the information about eventual voids. No. It is not accurate.
It's sorry. That's a big problem, because with the thermal camera you have a very poor spatial resolution, because you just have 640 pixels, and that will be hard to detect small defects. And his current, I thought it was 0.8 amps. It's pretty low, yeah. So perhaps you have to push it up to 8 amps or some higher current to see increase in temperature. So
Yeah,
I
I choose the ampere, the current, to have no influence in temperature. So we have this to equity.
Yes, I thought that where the section probably was affected by the generation of new voids, and once the section changes, the resistivity also will change and induce eventual thermal effect. So thank you so much for your kind lesson to